Okay, well, hey, thanks for being here. I know it's near the end of the day at the two-day conference here. Everybody's probably kind of tired, and some of you are probably jet-lagged like I am, and looking forward to hanging out and relaxing a little bit this evening. So appreciate you showing up and being here. I hope I can make it worth your while. My name is Dan Wilson. I'm here from Concur, principal architect there. And we're going to talk about switching from external load balancing to consul and Ingress with Kubernetes. Maybe not quite, because instead we're going to talk about how we tried to switch from external load balancing to consul and Ingress, and some of the challenges we ran into and where we're going to go to from there. So a little bit about Concur. We are in the business of controlling spend for companies. And at the same time, we make it easier as an employee to get reimbursed quickly for that spend when you're on the road. And our users expect our services to be available. So availability is super important to us. And speaking of users, we've been growing like mad, and it hasn't slowed down. In fact, it's accelerated since SAP acquired our business a few years ago. A little about me. Sorry. I've been at Concur forever and worn a lot of different hats throughout the years, thankfully, otherwise I'd be really bored. And I've been working on Kubernetes for about 1.5 years now, and I currently participate in the Federation SIG, and have been a contributor to that regard. So I love working with the product. A little bit about Kubernetes at Concur. This is a very high-level view. We have a lot of clusters and a lot of different locations. And in order to make it easy to deploy from a CI system onto those Kubernetes clusters, we wrote our own internal tool called Skipper. That's what the penguin is there. And what this does is it takes the deployment primitives as a result of our CI, the container, version of the container, how many copies you want to run, environment variables, and where you want to run it, whether you're running it in the US or EMEA or everywhere. And then it translates that into the different Kubernetes API calls, so that the services and deployment objects and whatever else are created on those clusters. And rollouts, blue-green deployments happen thanks to deployments. CI to us is a composable tier. So that could be Jenkins, it could be Drone, it could be Circle CI. It doesn't matter to us. The important thing is that it's really simple to do that deployment through a curl command at the end of the CI process. So zooming in a little bit on a single cluster, we've gone with a CoreOS deployment. We love the CoreOS system, super simple to get started. A lot of the things have been figured out for us already, like what version of etcd and Flannel and Docker all work together. We still make every cluster highly available with multiple etcd nodes and master nodes. We plug the pool of master nodes into external load balancers inside our data center so that API calls can be distributed to those masters. And if a service is deployed on our clusters, that service is also tied into external load balancing. I'll talk a little bit more about how we do that in a minute. We've pulled monitoring and elk outside of the cluster for obvious reasons. We have multiple clusters, and also if you had an issue with the cluster, it'd be nice to be able to actually use those services. So zooming out just a little bit to where we're looking at multiple clusters now in a single location. We tie those clusters into load balancing with a single endpoint. So a service that is being accessed would have a single DNS name, a single VIP, and a single pool. But inside of that pool are Kubernetes nodes from each of those clusters. So if a single cluster is having an issue, then requests can still get routed to the other Kubernetes clusters. And we made a conscious decision early on to go with this approach because the technology was still very new. Anytime you're dealing with new technology, there's some unknowns you could hit. We didn't want to risk those unknowns impacting our end users. And we wanted to go into a production state with Kubernetes as fast as possible. So that's why we went with this architecture. OK, so but how do you do that, right? How do you get those Kubernetes nodes plugged into a load balancer if you're in a private data center? We're in private cloud, or our own data centers in a lot of locations. We're also in public cloud. So we wanted it to work the same as much as possible. So we wrote our own little Kubernetes plugin. It's just a simple Golang container that runs on Kubernetes. It watches the API. Some of you may have attended some talks today talking about how to leverage the Kubernetes API. And that's exactly what we did. Kubernetes API is awesome. You can get a watch endpoint. You can get updates and fire off whatever events or changes that you need to make externally or inside the cluster. But how does this help you guys, right? Because you don't have our load balancing technology inside your data center. Chances are you don't have our abstracted API either. We have our own load balancing as a service inside our data centers that we're leveraging here instead of reaching out to the vendor's API directly. Well, you could do this yourself, too. If you have private data center needs, whether it's load balancing or logging changes to the cluster or whatever else, we created a little sample project on how to do this. It builds a Docker container. You can also use a sample project to test locally against Minikube. It's all the test scripts are set up for you. You could just add your business logic there. Or you could just write your own, too, and use this as an example. Just wanted to share as much as we could about how we did this inside our data center. OK, but what are some of the challenges we ran into with this design? Because clearly, it wasn't our design of choice if we wanted to move away from external load balancing. Well, one challenge is that the plugin has to be pretty smart because it's manipulating a single pool that has nodes in it from many clusters. So, first of all, you need to make sure that you're not messing with nodes from another cluster. And you can't use your node port that you get as a way of filtering that. You have to actually look at the IP ranges because those node ports are dynamic. But there is a chance of a collision that you could end up having the same node port from multiple clusters. The other thing is, when we tried to bridge this technology into the cloud, we decided to go with the software load balancer version of our vendor's hardware load balancer. And again, this was a conscious decision we made, mainly because our monolithic apps that we're also porting to the cloud relied on specific features for that load balancer. So we were going to be moving it into the cloud anyways as a software-defined appliance. And we wanted things to still be able to talk to each other from the legacy system to the new microservices systems as much as possible the same way inside our data center as it works in the cloud. Well, the software-defined load balancing doesn't look the same in the cloud as it does inside the data center. For one, there's a different load balancer for each availability zone. And then also, there's a global traffic manager that routes traffic to each of those load balancers. And in order to make this all work, we had to update our load balancing as a service API to be able to speak a totally different API to the global traffic manager. And we had to handle the fact that there was 3 load balancers that each service would end up getting plugged into. So just to show what this would look like with 3 services running on the 3 Kubernetes clusters, you're adding each one of those to every single load balancer. And then the vendor recommends, for high availability reasons, that you also add nodes from clusters in different region or in different availability zones. So we ended up having to run 3 copies of our integration on each cluster in order to plug the nodes into the 3 load balancers. And it just gets really messy, right? It creates a lot of spaghetti in our cloud environment that really shouldn't be there. OK, so we wanted a better approach. We started to write down our requirements. We wanted the environments to still look as much the same as possible in every location. We wanted to use the same technology in every location as well, if we could. SSL needs to be as close to our actual pods as possible and make sense for the workload. And it still needs to work with our own microservices, client certificate validation, and JOT validation. I'm not going to get into the details of how that works, just because I can't share it publicly. But just wanted to mention that there are those requirements that fed into this. OK, so physical load balancers don't work because there's no real equivalent in the cloud. This is like a nice classic car that's fast, but doesn't have all the bells and whistles that we need in a cloud, or like a really nice Beamer. And the cloud load balancing technology doesn't work for us because we can't run cloud load balancing in our data centers, at least not currently. So we started to look at consul and Ingress and pairing them together. So a little bit about consul. And when I'm talking about consul here, I'm talking about consul services and not consul key value store. Very different. The services allow you to take a set of systems and tie them into a single service. That then, when you do that, you get a DNS name in consul for that service that resolves if you use consul as your DNS server itself, or you forward to it from your existing DNS servers. Every time you ask for what the A record is of that DNS, you'll get one of the servers that are behind the name. And there's a bunch of logic that you can have consul do there so that it decides which node is responding the fastest and gives you that IP, or gives you the IP address of the node that's closest to you. So it's very valuable. It doesn't do anything at the higher networking layers, right? It's just giving you an IP address. And that's why it pairs really well with Ingress, because Ingress can do that layer 7 stuff. So if you wanted to route to a service based on the host header or based on the URI path, then Ingress handles that. Well, with each consul service, you'd have a unique DNS name. And with Ingress, you could look at that name and route it to the correct server. In our testing with Ingress, we saw a 2 to 3 millisecond overhead. We used the Nginx load balancing. Your mileage may vary. But just want to mention that we saw that. That seemed like a reasonable overhead for our microservices calls, as long as they weren't linear 1,000 calls that would create 2 to 3 seconds of latency. So the question came to be, is this the perfect match? So we put together an experiment using the technologies. And we leveraged a similar plugin to what you see in the community, a Kubernetes Plugin that would take changes to services and nodes and Kubernetes from the watch endpoints excuse me, and translate that into the API calls that you need to add and remove the correct nodes and node ports in console. Well, we ran into some issues. Also, you have to create the Ingress controller on Kubernetes and the Ingress resources themselves in order to make this work. And Ingress works the same way, actually, right? The Ingress controller is watching for the Ingress objects in Kubernetes and manipulating the load balancing rules dynamically. OK, so we ran into some problems. Accessing services across data centers was an issue for us because let's say my service is mysite.console.io. Well, if I'm in EMEA and I'm looking for a mysite.console.io, it'll give me the local location for that site. If I need to reach out to the US, though, there wasn't a way for us to do that because we hadn't set up clustering of console between all of our data centers. Console supports this, where you could say mysite.us.console.io, but we're just not set up for that yet. It wasn't a part of our rollout. Also, console DNS, by default, is set up with a TTL of 0. So what that means is every single DNS query is going to reach out to the console DNS server. Also, it's Paxos under the covers. And it's going to make sure that it is responding with a valid result by checking with the other nodes in the cluster. This takes time. So what we saw is on our untuned system, it was between 150 and 300 milliseconds of latency to do each console query, which that would definitely not fly. We've got some tuning to do there, so that's why we backed off a little bit. We haven't quite resolved those issues yet, but they are definitely solvable. Lastly, the Kubernetes Console plugin that you can find online. In fact, I found a bunch of different forks of it. I don't know why there's so many of them. There's like 10 or 20 of them out there. None of them supported console ACLs. So we had, again, needed to make some code changes there in order to support that. I'm happy to contribute those back. If somebody can tell me what the root Kubernetes Console project is to contribute them to, be happy to do it. Side benefit of using console is it stores the SRV record data. So not only do you get the DNS name, but you also get the port, the Kubernetes node port that the service is running on for each node. So if you're using a client library that knows how to read SRV records and get the port, you could skip the Ingress controller layer completely and hit your service directly, which would save you that 2 to 3 milliseconds, which might really matter for some workloads. OK, so having hit some stumbling blocks there, we decided to go and look at other alternatives. Like, is there some other way to solve this problem? And we went back to our load balancing tier. And we said, OK, why don't we couple what we're doing today with load balancing inside our data center with Ingress? So what this involves is having a lighter weight version of our plugin that instead of tying services into the load balancer for every service running, or entries into the load balancer for every service running on Kubernetes, it would just tie in the Ingress controller service itself into load balancing so that there's a small number of VIPs on the load balancer that then route directly to Ingress. And then Ingress from there would forward the request to the correct service based on DNS names. And we have the capability inside of our data center. We have a DNS API. So it would just be a matter of creating a CNAME for each service that would then point to either the main regional load balancer pool, or VIP, or the individual pool that the service is running on if it's not running across all clusters. And by doing that, we would get essentially the same thing we're getting out of console plus Ingress, but just using native DNS and using the native load balancing that we have in our data center. Another thought that we have here and what we're experimenting with is in the cloud environments, just leveraging autoscaling. Autoscaling can already add and remove nodes into load balancers, and it can do it so that your nodes can get tied into multiple load balancers as well. So why not just leverage what's available already there instead of having any plugin running on the Kubernetes clusters, and it's less for us to maintain overall. So this would end up making it so from a end-to-end developer team perspective, Kubernetes is acting the same way inside the cloud as it is inside our data center. They just have Ingress objects and services and deployments on Kubernetes. And the CNAME would then get tied into either the main load balancer or each individual load balancer, depending on what the needs are. OK, so to make that work, though, you'd have to have the multiple endpoints, one for each cluster, and then one for all of the clusters. And you'd have to have a way of creating that CNAME for each service so that Ingress can route the traffic. And then you'd have to create the Ingress objects for every service as well. Well, fortunately for us, it's pretty easy to do that because we already have an abstraction here. So adding in ingresses and a DNS API call to each deployment is just a matter of updating our skipper tool. So it would be clean and straightforward. So a little bit more about Skipper, because I've not yet open sourced Skipper itself. I'm definitely open to doing so, but I would much rather work together with people to rewrite something that makes sense for the whole community if it turns out to be something that would be useful. I've heard a few other talks today and yesterday with similar needs that we have, so it might make sense for us to do that. Also, I've been making Skipper thinner as much as I can, so it's less code for us to maintain, and it gives value back to the community by contributing the features that we've rolled into this product internally into Kubernetes Federation. And that's really the direction we want to go long term, is to just leverage Federation. Everybody knows, though, that Federation works great on cloud providers right now, but not so much inside your data center. So that's what I have. I'd be happy to take any questions. I'm sorry.
Your ingresses, how are you doing SSL?
Yeah, so the ingresses terminate SSL using certificate, and where needed, they can reestablish SSL to the individual pods as well. So.
How are you managing getting this key files into the Ingress control?
So for us, we have individual DNS spaces that we own, and we're able to wildcard the certificate internally with an internal DNS name at the Ingress layer, and then use individual certificates from there for our client certificate authorization.
I'm compared with cloud station using Vault for this, so that's a real chapter. Someone's doing that as well.
OK, yeah, I'd be happy to talk after. Oh. Yes?
I was curious then, who's the consumer of the console DNS in that setup? Is that the public DNS for your services or something else?
OK, so the question is, who's the consumer for the console DNS in this situation? It is not external consumers. It's internal consumers of the console DNS. All of our external calls go through a separate tier of API gateways in our data centers, and then from there, it would end up hitting the console DNS. Yeah. Great. Happy to take more questions if there are more. All right. Everybody looking forward? Thank you.